Number 5 has a 4,000 pound concrete block sitting on a 3,000 pound flatbed truck. Maximum tractive force of the truck so the concrete block does not start sliding. Alright, so this one again is a little different than others we've worked before, so we got to think through what's happening. We're given mu sub s, mu sub k, we're given weights of the two objects. We're told that we're going to need two free body diagram, kinetic diagrams. So let's just figure out what we want to do here. We don't know attractive force. We know it's not, we don't want it to start sliding, so this right here is the key. We want to look at impending motion. Okay. When I first look at this problem, I'm still not positive on exactly the approach to take, but I'm going to start working through it and identifying some unknowns, and hopefully I'll end up with enough equations to solve for those unknowns. So if we're going to look at the friction, the sliding impending motion between the concrete block and the bed of the truck, we need to draw a free body diagram of perhaps the concrete block. So let's do that first. The other choice would be just the truck. Alright, so here's the concrete block isolated, free body and kinetic diagram. Okay, the forces on this are obviously the weight, the normal force, and let's see, it's a 4,000 pound. Okay, what is accelerating the concrete block? If the truck is accelerating forward and this concrete block is not sliding, then we're going to have a friction force that's opposite the impending or relative motion between the concrete block and the truck bed if it did. So if the truck is accelerating forward this way, the concrete block is going to want to slide, or want to stay there sort of, and slide backwards relative to the truck, so that friction force is going to be forward. Okay, we know sort of that's going to happen because we've got attractive force. The concrete block is going to have a mass times acceleration in the forward direction, so the only force in the horizontal direction is the friction force, and so it has to be associated with this mass times acceleration. Okay, and we know for impending motion the friction force is mu sub s times n. So it looks like that was a good choice. We can, from here in the y direction, say that n minus w equals 0. N is going to be 4,000 pounds. And in the x direction, we can say F, let's label that force of friction, equals ma. That's mu sub s times n equals ma. And we'll go ahead and solve for a right here to be mu sub s n over m, which is 0.4 times 4,000 over mass, 4,000 divided by 32.2. So really, our acceleration, the weight is going to cancel out. The 32.2 is going to come to the top, and it's just 1.4 times 32.2, 12.88. Okay, so now we draw a free body diagram of the entire system, and I'm just going to draw something like this: truck plus concrete block. Let's see, let's go with green this time. Total weight, normal force, traction force, and it's going to have a mass times acceleration. Alright, we do not include the friction force because it's internal, because we've drawn a free body diagram of the whole system. So this will let us easily solve for our traction force. It's almost too easy. The mass is going to be 4,000 plus 3,000 over 32.2. That's pounds, that's foot per second squared, times our acceleration, 12.88. Alright, so it's this stuff multiplied together. If you remember, the 12.88 over 32.2 was actually just our point, came from our 0.4 times 32.2. So it looks like it's going to be 0.4 of 12,000, but we'll punch it out, or 7,000, excuse me. 7,000 divided by 32.2 times 12.88, 2,800 pounds. So there's our traction force. Although it wasn't obvious how to start, we chose to isolate one of the things that had the friction force on it. We had to identify impending motion and then go back and take that acceleration and apply it to the whole system. If we had any more tractive force than that, the concrete block would start sliding off the back of the truck.